Hello, today we'll be covering rational exponents from Blitzer's Introductory and Intermediate Algebra text for college students. My name is Professor Shannon Gracie. Here we go. Today we'll be learning how to use the definition of a base raised to a fractional exponent. So rational comes from ratio. So ratio is a fraction. So rational exponents is what we're covering today. So here we go. Let's warm up. Pause the movie. See how you do. Okay, let's see how you did. This warm up is geared towards, you'll be using properties of exponents, which for rational exponents are just like you learned in chapter 5 for exponents that were integers. And now what we'll be doing is having to add, subtract, and multiply these fractions when they are exponents. So same rules apply. You need to get a common denominator. So here this gave us 8 minus 3, my apologies, 4 minus 3 all over 8, because 4 eighths minus 3 eighths gives us one happy fraction. And we'll end up with an end result of 1/8. How'd you do? Awesome. Okay, so here we go. We need to first raise this quantity to this power. So if you recall, when you are raising a power to a power, you multiply powers. So this 2 has kind of an invisible 1 power. So we'll have 2 to the 1 times -3 is -3. And then times x to the 3 times -3 is -9. Now we have the same base, and we've got this negative exponent here. So remember that 2 is can be written as 2 to the positive 3. We'll have x to the 2 minus -9. And whoops, this y had a 5 on it, and y to the 5th. So what we'll have at the end of the day is 8 from the 2 cubed, x to the 11th, y to the 5th, and we're all done. So let's move right along to the definition of a raised to the 1 over n. All right. If the nth root of a represents a real number and n is greater than or equal to 2 and is an integer, then it turns out that a raised to the 1 over n is equal to the nth root of a. So the way I remember this is power over root. So if you take a look at doing it exactly, oops, as it's translated, this is the nth root of a to the 1. So the 1 is the power on the a, and n is the index of the radical, which of course is just the nth root of a. So if n is even, a must be non-negative, and if n is odd, a can be any real number. So here we go. Here's an example. So we want to use radical notation to rewrite each expression. So this one is going to be the square root. So remember, with square root, the index is implied, but we can go ahead and write it like this exactly. So this just means the square root of 400, which, as you know, is the square root of 20 squared, which just gives us a result of 20. So we were able to simplify that one. And remember, this was power over root. All right, so here we are. We now have 7xy squared. And then that's going to be to the 1 power raised to the cube root. So here, power over root. And we can just write this guy as the cube root of 7xy squared. Next up, we have negative 32 raised to the 1/5. So what do we do? Good, it's going to be negative 32 to the 1 power, and that'll be the 5th root. So power over root, and we'll have the 5th root, now negative 32, which is the 5th root of negative 2 to the 5th. And remember, once you match the power inside to the index, you just get a result of negative 2. So we were also able to simplify part C. Now our next job is to go the other way around. So again, here we could write this to the 1 power. So then doing our power over root, we're going to have 12st raised to the 1 over, good, 4. So power over root. And we're done. Okay, so now we have, again, this could be written to the 1 power. So we'll have 3z squared over 10 raised to the, awesome, 1/3. So the power to this stuff was the 1, and the root was the 1/3. So it's a cube root. We can't simplify any of that. All right, and then this guy, remember there's kind of an invisible 2 right there. So you've got your power over root. So this will end up being 5 times xyz raised to the 1/2. Power over root. And, hopefully you'll get to the point where this is seamless for you. When I see the square root of 9, that means the same to me as 9 to the 1/2. So that's where you should aspire to go. Okay, so here we go. Next up, this shouldn't be too much of a stretch for you since I already clued you in on the power over root business. But if the nth root of a represents a real number, m over n is a positive rational number reduced to lowest terms, and n has to be greater than or equal to 2 in an integer, then it turns out that a raised to the m over n is equal to, so again, you can do power over root again. You can do this a couple different ways. You can view this as the nth root of a raised to the mth power. So this means that you would first evaluate the nth root of a, then raise the result to the mth power. You can also figure this out as a to the m, so you're first raising a to that mth power, and then you're evaluating the nth root of the result. So first raise a to the mth power, then evaluate the nth root of the result. It just depends on what is easier for you. And some problems lend themselves to one method and other problems lend themselves to the other. Okay, so here we go with some more examples. So with this first part, we're going to use radical notation to rewrite each expression, and then we'll simplify if we can. So remember, what do we have? Good, power over root. So this will be the fourth root of 16. Now we have to think about this, okay? Is there a fourth root of 16 that we can evaluate? Yes, there is. So I'm going to write this as the fourth root of 16 raised to the third power. I'm using that one. So again, power over root. So the reason I wrote this one like this, and a lot of them are going to end up this way, is because 2 to the fourth is 16. And we're able to match the index on the radical, and then we'll be cubing that result. So this will be 2 cubed, which is, good, 8. Okay. Now, part B, this one I have a wee bit of a typo. So what we're going to change this problem just a little bit, and we're going to rewrite this as negative 729 raised to the 2/3. So when we do this one, it turns out that negative 9 cubed is 729. So I'm going to write it the same way. I'm going to say the cube root of negative 729, all that squared. And again, this is just going to take practice for you so that you can determine, which way to write it. But this is often the way. So here we'll have the cube root of negative 9 cubed squared, which will be negative 9 squared, which is positive 81. Okay, next up, part C. So here, 9 is a perfect square. So remember, power over root, so it ends up that this is equivalent to the square root of 9 raised to the 5th. The square root of 9 is 3, so we'll be raising that to the 5th, which is 243. And again, we can go ahead and write that little 2 there right now if you need to. So actually, I've been doing the power in yellow. So power over root. Okay. Rewrite each of these with rational exponents. So we'll be going the other way. So this here, the power good is 4. The radicand is 12. So we'll have 12 raised to the 4 thirds. So this was our root. Keep forgetting which color we were doing. Oh, the root was in blue. Okay, so our power is here, and our root is here. And that one, you know, 12 is not a perfect cube. If I raise 12 to the 4th, I am not going to get a perfect cube. So, so this guy we're done for now. We'll learn some other stuff later. All right, so next up we will have x over y to the good 4/5. The power was 4 and the root was 5. And that one we're done. There's nothing more that we can do. We've done our job. And here we'll have 11t to the good 3/2. Remember, there's an invisible 2, an implied 2, and a square root. So the power was 3 and the root was 2. We're all done. You need to make sure you put parentheses, you know, around whatever was in the radical. Okay, now we come to the definition of a raised to the negative m over n. So if m over n is a non-zero real number, then a raised to the negative m over n is 1 over a to the m over n. Okay. So there's a couple more examples, a few more examples to do on this guy. So first step, rewrite these without negative exponents. So this will end up being 1 over 144 to the 1/2, which is 1 over the square root of 144, which is 1/12. This guy will be 1 over negative 8 to the positive 2/3. Good. Which will be, notice that negative 8 is a perfect cube. So we would want to write this as the cube root of negative 8 and then square the result. So the cube root of negative 8 is good. Negative 2 will be squaring that result. And at the end of the day, we get 1/4. All right, 32 to the negative 3/5 is 1 over 32 to the positive 3/5. Now, 2 raised to the 5th power is indeed 32. So we would rewrite this as the 5th root of 32, and we're going to raise that result to the 3rd power. So we will have the 5th root of 2 to the 5th, and then that will be cubed. So we'll get 1 over 2 cubed, which is 1/8. Okay. And, you know, some of these start to get a little bit confusing. Let's just kind of highlight what goes with what. The cube root of negative 8 has a result of negative 2. Over here, the 5th root of 32 is equivalent to the 5th root of 2 to the 5th, which was 2. The square root of 144 was 12. All right, so properties of rational exponents. So be careful now so that he doesn't have to come up with, 4 different variables. We've been saying m over n in the other definitions. Now m is a rational exponent. So m is a fraction and n is a fraction. So if you have this case, it turns out all the rules are the same. If you have the same base and you're multiplying, you add the exponents. Same deal, except you're going to be adding fractions. All right, same base and you're dividing, good, subtract the exponents. When you're raising a power to a power, you multiply the exponents. When you have 2 different bases raised to the same power, you can raise each base to that power. And when you have a quotient raised to a power, you can raise the numerator to the power over the denominator to the power. Alrighty, so here we go. We're going to use properties of rational exponents to simplify each expression. Now, here we're going to assume that all variables represent positive numbers. That means that we're not going to have to put absolute value bars around any of our answers, right? So, here we go. We have the same base and we are multiplying. So what do we do with the exponents? Good, we add them. So we'll have 5 raised to the 2/3 plus 1/3. Well, that'll be 5 to the 1. 2/3 plus 1/3 is 3/3, which is 1. And we'll just get a result of 5. Now we have a product to a power. So this is going to be 125 raised to the 1/3 times x to the 9 times 1/3. Power raised to a power, you multiply. And then y to the 6 times 1/3. So this one, 125 to the 1/3, you can either think of that as the cube root of 125. You might recognize that 125 is 5 cubed. You're raising that to the 1/3. So this here, 125 is 5 cubed. And then this x, 9 times 1/3 is 3. And then 6 times 1/3 on the y will be 2. Well, do you see this will just be 5 to the 1 because we're doing 3 times 1/3. Oops, times x cubed y squared. So we will get 5 to the 1, which is 5, x cubed y squared. And that's our end result. And then part C, this will be 2 to the 4th y to the 1/5 times 4 over y to the 3/10. So 2 to the 4th is 16. We'll have y to the 4/5 over y to the 3/10. This will give us a result of 16 y to the 4/5 minus 3/10. We have the same base and we're dividing. So we subtract the exponents. So now it gets a little tricky. We got to get a common denominator. So if I multiply 4/5 by 2 over 2, I'll get the common denominator of 10. So this will be 16 times y to the 8 minus 3 all over 10. So that'll be 16y to the 5/10, but we can reduce that to 16y to the 1/2. Or you could write this as 16 times the square root of y. Typically, you want to end up with what the problem started with. So if it had rational exponents, this guy here is probably the better answer, the first one. But these are equivalent. So read your directions carefully. Simplifying radical expressions using rational exponents. So in this case, when the author starts with the radical expression, he wants you to end with the radical expression if it doesn't completely simplify. So rewrite each radical expression as an exponential expression with a rational exponent. Simplify using properties of rational exponents. And then rewrite in radical notation if rational exponents still occur. So that's what we actually did on that last problem, that last step. So here we go. This one here, the base is xy. It's raised to the 21st power, and it had a cube root. So again, power over root, power over root. So I can simplify this guy to be xy to the 7th, which of course is x to the 7th times y to the 7th. And we're done. All right, so now the square root of 3 we can write as 3 to the 1/2, and then we've got times 3 to the 1/3, again power over root. I have the same base I'm multiplying, so that would be 3 to the 1/2 plus 1/3, getting a common denominator. Multiply the 1/2 by 3 over 3 and the 1/3 by 2 over 2, and I end up with 3 to the 3 plus 2 all over 6, which gives me a result of 3 to the 5/6. And then I take that one last step and I get the 6th root of 3 to the 5th, which, you know, we could raise that 3 to the 5th power, so we could get the 6th root of 243. So either one would work. Okay, so part C, we have a to the 3/4. Actually, let's do this. We've got, do you see a cubed b cubed is a times b cubed, and then that's in a 4th root, and this is the square root of a times b. So we will have ab to the 3/4 divided by ab to the, awesome, 1/2. We have the same base of a times b, so we can say that that's the same as ab to the 3/4 minus 1/2, which is ab. Again, we need to get a common denominator, so if I multiply the 1/2 by 2 over 2, I'll get 3 minus 2 all over 4. So I get ab to the 1/4, and putting that back into radical notation, I'll have the fourth root of AB. So I know it still looks a little complicated, but I think you'll agree that it's less messy than what the problem originally started as. And we're all done with this section. Have a great day. Don't forget to do some of the homework problems so you submit your knowledge. Bye.